Let's go, Nashville!
It's time for Maths with Mr. Thomas.
Chapter 12, lesson number 5. We're moving on now to look at de Moivre's theorem. Dum dum dum. Let's say we have a complex number. We have z equals r bracket cos theta plus I sine theta. That's our complex number, and when it's written in that form, that is known as polar form. Brilliant, that is a polar form. Let's say we wanted to work out z squared. Meatloaf. How would you work out z squared? Brilliant, it's just going to be z times z. So we'd have our r bracket cos theta plus I sine theta multiplied by the r bracket cos theta plus I sine theta. And to multiply our complex numbers together when they are in polar form, you know from the last lesson what you can do to multiply two complex numbers in polar form. Multiply the moduli and add the arguments. So the modulus here is r, the modulus here is r. You'd multiply them together to get r squared. And then add the arguments. You've got a cos theta and a cos theta, so it's theta add theta, so you'd have cos 2 theta. And the same with sine theta, you'd have I sine 2 theta. That would be our z squared. Woo! If we want to work out z cubed, Patty Russo, what would you do? Brilliant, it is going to be z squared times z. So we would have this r squared bracket cos 2 theta plus I sine 2 theta multiplied by z, the r bracket cos theta plus I sine theta. If we do that once again, we are, hello! We're going to multiply the moduli and add the arguments. So we'd have our r squared times r, so we'd end up with r cubed. And because we've got cos 2 theta and cos theta, we just add the arguments, so it's cos 3 theta. And the same with sine, we'd have I sine 3 theta. Just add the arguments. Let's take that one step further, but you're maybe seeing a pattern already. If you want to work out z to the power of 4, Kazim Sultan, what would you do? Brilliant, you are going to have your z cubed multiplied by z, or you could do z squared times z squared. Either way, you get the same answer. Going down this route of z cubed times z. So z cubed was r cubed bracket cos 3 theta plus I sine 3 theta. And we're multiplying that by the r cos theta plus I sine theta. Just multiplying that by z. Once again, you're going to multiply the moduli. So we would have the r cubed times r, which would be r to the power of 4. And then we've got cos 3 theta and cos theta. Add the arguments together. So 3 theta add theta is 4 theta. Brilliant. And we would have I sine 4 theta. Brilliant. If you have a complex number expressed in polar form, so if z equals r bracket cos theta plus I sine theta, the result, how would you work out, say, your z to the power of 5? What do you think that would be? Brilliant. Or if it was z to the power of 6, what would that be? Brilliant. You're noticing the pattern. Here we've got a z squared, so we've got our r squared. Here is z cubed, so we've got r cubed. Here we've got z to the power of 4, so it's r to the power of 4. So we would have, if it's z to the power of n, so n would just be some number, you would have r to the power of whatever that number is. And for the argument, you know you're going to have your cos and your I sine, but here, if it's z to the power of 2, we've got cos 2 theta. Here, if it's z to the power of 3, we've got cos 3 theta. Z to the power of 4 gives cos 4 theta. So if it's z to the power of n, you're going to have cos n theta. And then plus your I sine, same thing, n theta. Woo! Really, the result of the power of a complex number when it is in polar form, just this. It's known as de Moivre's theorem, named after the mathematician Abraham de Moivre. Yo, check out my funky hairdo, darlings. See ya. It's also valid for negative and fractional powers of complex numbers in polar form. So let's try a couple of examples where we are applying de Moivre's theorem. Bum, bum, bum. Example 1, write the complex number z equals negative root 3 plus I in polar form. Part B, express z to the power of 4 in the form x plus yi, where x and y are real numbers. And C, show that z to the power of 6 plus 64 equals 0. So we're starting off part A with z equals negative root 3 plus I. You know from the previous lessons, what you want to do is you're wanting to take the real part and take the coefficient just of I, take the imaginary part as well, and you're wanting to plot that on your Argand diagram. Yeah. So here we are going to plot. We've got this negative root 3 and we've got 1i. So we would have 1. So we're wanting to plot negative root 3, 1. So on your Argand diagram with the x and the y axis being your real and imaginary axes, we know we're going to go back root 3, so we're going back, so it's negative root 3. I'm just writing that as root 3 because that's the length of that line, but I'm going back to the left, root 3, and positive 1 means we're going up 1. This is what we're going to write down for z, so this will represent that complex number on the Argand diagram. To work out the modulus, well, that's really just the length going from that point that we plotted to the origin. And to work that out, you would use Pythagoras. Brilliant. So here we would say that r would equal, and it's the square root of that root 3 squared plus 1 squared. Work that out, and it's the square root of 3 add 1, which is square root of 4, which gives you 2. That would be the length of that line. For the argument, just remember your argument goes from 0 all the way around to 180 degrees, or 0 around to negative 180 degrees. In here, which is where this line is, we know that that's going to be between 90 and 180. And the best way to do it is to work out the size of the acute angle. So work out this angle first of all. So we're going to just call that alpha. So we can say then that tan alpha is going to equal, because we've got this right angled triangle, tan is going to be the opposite over adjacent. So that will just give us a 1 over root 3. To work out alpha then, well, you're going to have tan to the minus 1 of that 1 over root 3, which works out to be, brilliant, 30 degrees. Fantastic. Meaning then this acute angle here is 30 degrees. So that angle's 30. So how far would it be from the 0 round to that line? Well, you're just doing 180, take away 30, which will give you 150 degrees, which is what you expect because you know you're going to be between the 90 and 180. Therefore, we can say the modulus is 2, and the argument is 150 degrees. Woo! We are asked to express it in polar form, and we know that's going to be when we have z equals r cos theta plus I sine theta. So if you take that slightly further, Paul Crook, what would you do? Brilliant. All you do is you replace r with 2 because that's the length of the modulus. That's what the modulus is. That's 2. And the argument is 150 degrees. So we can say that that's going to be cos 150 degrees plus I sine 150 degrees. Woo! Part B, express z to the power of 4 in the form x plus yi, where x and y are real numbers. So what we've got from the last slide, we know that in polar form z is going to be the 2 bracket cos 150 plus I sine 150. If you want to work out a power of a complex number, you will use this, which is de Moivre's theorem. And what de Moivre's theorem states is that if you have z to the power of n, all you do is you do the r modulus, the r to the power of whatever n is, and you multiply the argument by that n. So here we're wanting z to the power of 4, which means then that we will have, if this is the modulus 2, we're going to have 2 to the power of 4. We want z to the power of 4, so it's the modulus to the power of 4. And with the argument, with 150 degrees, what we do is we multiply that by 4. So we'd have 4 times the 150. And then plus I sine, and again it's 4 times the 150. If you work that out, 2 to the power of 4 gives you, Mark Alexander, brilliant, it gives you 16. And if you've got 4 times 150, John Michelli, brilliant, it would give you 600 degrees. So you've got the 16 bracket cos 600 plus I sine 600. Woo! However, if you look at this question, it says express z to the power of 4 in the form x plus yi, which means we're not wanting it in this polar form. So how do we change it into the form of x plus yi? What could you do? Marion Raven, can you help us? Yes. Brilliant. Good. All you're wanting to do with that is, well, leave the 16 as is just now, but just work out the value of the cos of 600. If you work that out either using your exact value triangles and cast and so on from higher, or just banging it into your calculator, you end up with negative 1/2. And if you work out sine of 600, you will get negative root 3 over 2. So that will be the coefficient of I. And from there, all you can do next is Randy Flowers, finish it off. Brilliant. Just multiply the brackets. So 16 times negative half will give you the negative 8. And the 16 times the negative root 3 over 2i will give you negative 8 root 3i. So that is us expressing z to the 4 in the form x plus yi. Part C, show that z to the power of 6 plus 64 equals 0. So where do we go from here? Well, once again, from part A, we know that this is our complex number in polar form. We know if we want the power of a complex number, we're going to be using the Moivre's theorem. So if we have z to the power of 6 add 64 equals 0, well, we're asked to show that. So really what we want to do first is work out z to the power of 6. So z to the power of 6 will equal Cici Coletti. What do we do? Brilliant. From here, because we're replacing real n with 6, we know we would have the modulus to the power of 6. So we'll have 2 to the power of 6. And with the argument, what we're doing again is we're replacing n with 6. We're multiplying whatever the argument is by 6. So the argument's 150, so we're going to have cos of 6 times 150 plus I sine, and then 6 times 150 degrees. From there, well, we know 2 to the power of 6 is 64. And if you do 6 times 150, that gives you 900. We're asked to show that z to the power of 6 add 64 equals 0. Well, where do you think we go from here? What do we do next? Perfect. What you can do after that is you could work out the value of cos of 900 and the sine of 900. Cos of 900, you could think about that with the graphs. You could use a calculator and use cast. Think about it whichever way you want, but that will give you -1. And the sine of 900 is going to be 0, which means then that we've got 64 times -1, which is -64, and then we've got 64 times 0 times I. Well, because the zero's in there, well, it just works out to be 0. So it leaves us with this -64. So z to the power of 6 works out to be -64, meaning then that z to the power of 6 add 64 would give you -64 add 64. And that works out to be 0! Perfect. And that is us showing that z to the power of 6 add 64 gives us 0. Woo! Example 2, let z equal 1 plus root 3i and w equal -2 root 3 plus 2i. First of all, write z and w in polar form. B, hence express z to the power of 3 w squared in the form x plus yi, where x and y are real numbers. And C, hence express z to the power of 9 over w cubed in the form x plus yi man, where x and y are real numbers. This first part here, expressing z and w in polar form, I've done that in the last few examples. I did that with example 1. I'm not going to put more of that in, it just takes up more time in this video. You should be able to do that because all you're wanting to do is just plot 1 and root 3. You'd work out the modulus, work out the argument, and then you can write that in polar form. Really, it can be shown that your z would equal to bracket cos 60 plus I sine 60 if you go through all the working with that. If you want an example, look back at the first example or the other video. Same with w, you would plot the -2 root 3 and then 2, work out the modulus, work out the argument, and what you end up getting is that 4 bracket cos 150 plus I sine 150. Again, if you want that, just look back to the lesson 12.3 or look back to the first example where I will show you what to do. But this lesson's all about the powers. So part B, hence express z to the power of 3w squared in the form x plus yi, where x and y are real numbers. Well, we know that we've got z to the power of 3, and we know z is a 2 bracket cos 60 plus I sine 60. So really we want to work out z cubed. So to work out z cubed, well, what we would use is de Moivre's theorem. Because we've got this complex number and we want to work out the power of the complex number, that's what we would use. So you remember, if you've got z equals r bracket cos theta plus I sine theta, all you do if you want z to the power of n is you have the modulus to the power of n and you multiply the arguments by n. Meaning then, if we've got 2 cos 60 plus I sine 60, we would have 2 to the power of 3 for z to the power of 3. And then we would have brackets cos of 3 times 60 plus I sine 3 times 60. 2 to the power of 3 is obviously 8, and the 3 times 60 is 180. 180! First, w squared, do the same thing. So, because we've got w to the power of 2, we know we'd have the modulus to the power of 2. So we'd have that 4 to the power of 2, because that's what w is. So we've got 4 to the power of 2, and then we'd have cos, well, it's 150, so we times that by the 2. So we'd have cos bracket 2 times 150 plus I sine 2 times 150. From there, 4 squared is 16. 2 times 150 is 300. So we would have w squared as 16 bracket cos 300 plus I sine 300. We are wanting to work out z to the power of 3 w squared. So we're really wanting in polar form, we're wanting this 8 bracket cos 180 plus I sine 180 multiplied by the w squared, the 16 bracket cos 300 plus I sine 300. So we have this complex number in polar form, we have this complex number in polar form as well, and you know from the lesson that we've already covered is to multiply complex numbers in polar form, multiply the moduli and add the arguments. So we would have the 8 times by the 16, which gives you 128. Brilliant. And we would add the arguments. So we've got the cos of 180 and the cos of 300. So 180 add 300 means we'd have cos of 480. And it's the same with sine. So we'd have I sine 180 add 300 would also give us 480. Woo! So multiply the moduli and add the arguments. Where do we go from there? Well, what we can do after that is if we're wanting it in the form of x plus yi, we can just evaluate, we can work out cos of 480. Either do what you did in higher using exact value triangles, cast, graphs and so on, or you could use your calculator. But the cos of 480 is negative 1/2, and the sine of 480 is root 3 over 2. After that, go on CC once again, what do? Multiply the brackets. Brilliant. So multiply the brackets. 128 times negative 1/2 will give you negative 64. And if you have the root 3 over 2i, multiplying that by 128 as well, that will give you 64 root 3i. And that will be your complex number in the form of x plus yi. Part C, hence express z to the power of 9 over w cubed in the form x plus yi, where once again x and y are real numbers. So, using what we had in part A, we know z and w both in polar form, so we want to work out first of all z to the power of 9. Using de Moivre's theorem, if we have z to the power of 9, we've got the modulus to the power of 9. So for z, modulus is 2, so it's a 2 to the power of 9. It's cos of 60 and sine 60, so we're taking the arguments, the 60, and multiplying them by the 9. Work that out, 2 to the power of 9 gives you 512, and if you do 9 times 60, that means you will get cos for 540 plus I sine 540. Do the same thing with w cubed. So for w cubed, you are going to have, well, w is the 4 bracket, so the modulus is 4, so if we want w cubed, we've got the modulus to the power of 3. Just using the de Moivre's theorem. The argument is 150 degrees, so for w cubed we multiply that argument by 3. So we do 3 times 150 and then again I sine 3 times 150, meaning you will end up with 64 bracket cos 450 plus I sine 450. So we've worked out z to the power of 9, we've worked out w cubed, hi-fi us. What we do next is we're wanting to work out the z to the power of 9 divided by w cubed. Well, really, if you take these numbers, which are in polar form, really what we've got then is the 512 bracket cos 540 plus I sine 540 divided by the 64 bracket cos 450 plus I sine 450. Here we're wanting to divide the complex numbers in polar form, so again, you're just wanting to think back to the start of this chapter. When we're dividing our complex numbers in polar form, we divide the moduli and we subtract the arguments. So 512 divided by 64, go on, meet once again, what would it be? 8. Perfect. And with the arguments, you'd have 540 take away 450, which works out to be 90. We are wanting to leave our answer in the form of x plus yi. We don't want it in polar form, so taking that a stage further, we just need to work out cos of 90 and sine of 90. Cos of 90 works out to be 0. Brilliant. And sine of 90 is 1. Brilliant. So we'd have 8 times 0 plus 1i. Multiply with the brackets, and you know 8 times 0 is 0, and 8 times 1 times I, you could just write as 8i. Woo! So that would be our answer. That's it for De Moivre's theorem, working out the power of a complex number. Try some of the questions in the Unit 3 booklet on page 63. Check your answers as you go. Any problems, let me know. Have fun, and don't stop rocking. Bye.